I'm going home for the weekend, so nice. Sacrifice your long, I think it's yeah. Yeah. How they're concerned about the number of we're going to do and I can set it up so that it just admits people automatically. Yeah, that would be great. It's just weird because I feel like it's just all the craziness. Not really sure. It might have pulled out. But if anything, it was $6. Did you guess? I have the. I took 105. It's like the name. Some dude was that one thing.
Yeah, I just noticed.
Good afternoon, everyone. I have a mic on the side of my face mask. Someone suggested that might allow you to hear things more clearly. I don't know if that's the case. If it seems to only make things worse, please let me know, and I will simply attach it to my shirt. So let's go ahead and get underway. I'd like to begin with prayer. Is there a volunteer to help us out with that? Anyone? Please.
Dear Heavenly Father, we're very grateful for this day, and we're grateful that we can meet here today for our biochem class. And please bless us that we'll be able to work hard and put our best foot forward in class, and that we'll be able to learn a lot today as we listen. And we love you and say these things in the name of Jesus Christ. Amen.
Amen. Thank you. Appreciate that. Okay. Is that better? Worse? Doesn't matter to you. But maybe online, that doesn't make a difference.
Yeah, it's like.
Okay. Yeah, okay. First, a few things to begin with. I'm going to distribute a copy of the hard copy of the syllabus and schedule. Please take one. or more. Also, I have a sheet here regarding privacy. This is FERPA regulations. We've gone over this in the last 2 classes, so hopefully you understand what this is, but it is asking for your permission to return graded materials to to bins that are located beneath the display case that will be located in the Benson building, and it is designated for our class. And so quizzes, group quizzes will be placed there, exams will be placed there. Let me note that with exams, there is a cover sheet, and consequently people can't see the scores without deliberately opening up the exam and looking at it. Nevertheless, given that it's in a public place, you can choose to allow us to do that, or you can opt to come to my office as at a time that's mutually convenient and receive your graded material. So it's your choice. Please choose what you're comfortable with and sign this, and you can either pass it to the end of the aisle or return it at the end of class. If I could get my TAs to pass this. So this is Jason and Rebecca, their TAs. So this is perhaps the first time you've seen them in person. Here they are. We have one other, Justin Ballard. I don't see him right here at the moment. Sometimes he comes a couple minutes late. All right. Yes, sir.
Just real quick, I just noticed some people said it's so muffled. I was thinking if you flip it upside down, so the mic's not touching your shirt, it might make it better. Like flip it on the same place, but just turn it 180 degrees. Just,
Try that. The problem is that they've taken the little sponge thing off of it, so it picks up every little movement that one makes. They do this for sanitation purposes, but is that better or worse? Sounds louder to me. It's usually not the how loud the sound is, but how clear the sound is. Okay. All right. I did want to remind you that at the beginning of each class, I will write on the board things to know. These are the topics that we will cover today that will appear on exams. So other materials that we might talk about today will not, but these potentially will. So I haven't written the exam, so I can't tell you exactly what will or will not be on it, but these are candidates for questions on the exam. I've had a couple emails asking about how to prepare for the exams, and so let me spend just a minute and talk about that. People have asked if they should solve the problems or do the problems at the end of the chapter, or those problems within the chapter as a way of preparing for the exam. While that's probably useful, the questions on the exam may not reflect in any recognizable way the questions at the end of the chapter. So if you do it, it's only for your own personal benefit, but I wouldn't say that that is the way to prepare for the exam. I would pay close attention to what's listed on the board as we go through topics. If you really feel the need to consider things in advance, like well in advance, a week or two, I'll be happy to suggest what those things to know will be for future lectures. But by all means, you should know these. Also, I will have a study guide that I will prepare and have available hopefully about a week prior to the exam that will detail those topics asked about on the exam and the number of questions related to each of the topics on that study guide to give you an idea of how to apportion your time, how to focus on those topics that are going to be most heavily asked about. People have asked me to put up a prior exam. I will not do that. I've done that before. Then people study that exam, they study it exhaustively. They know all of the answers to those questions, and none of those questions appear on the current exam. And then they are angry because they have spent their time and effort studying that prior exam. So I'm not going to put one up. However, I have already put up some sample questions from previous exams to give you a sense of the level of detail, the type of questions that could appear on an exam. So please look at those, but please understand that those will not be questions on a current exam. Okay. Questions about this? So how do you study for an exam? So let me recommend that in addition to looking at these things, that you do spend time reading the material in the book, that you discuss this with others in the class or others who may be friends who have had the class or may be knowledgeable in the subject, to take turns explaining things to one another so that you can identify where you may have gaps in your understanding, but also to consolidate those things that you do know. You'll remember them better if you have explained them in detail to someone else. For those topics on which we will spend a great deal of time, as an example, hemoglobin, probably 40% of the questions or points, at least, on the exam, the first exam, will be about hemoglobin and the regulation of oxygen binding. In those situations where there are many questions about a particular topic, it will be important to know the details. And by this, just as a measure of this, you should be able to teach this topic to somebody else without notes, okay? So it is to actually have a working knowledge of it, not just a few memorized facts about hemoglobin and a few other central topics that we will spend time on. Again, if you want to know what will be asked about on the exam, I'll be happy to tell you. It's just that it doesn't solve the problem of having to know the material well enough to answer the questions. I would say that my exams are not, that I don't try to trick students. I don't ask about things that haven't been discussed in class. I don't try to write questions in such a way that they are tricky. Nevertheless, for core topics, the level of detail is quite substantial and requires a fair amount of study to be able to master that material. Okay. Yes?
Maybe question, did your questions include more calculations type questions, or conceptual memorization things?
We will have a few calculations, so not too many. So it's not math driven the way that, let's say, Chem 105 or 106 was. There are conceptual questions, some of which will require you to extrapolate. That is, you will know something and be able to apply it to a new situation. So you understand, let's say, separations, how you separate one molecule from another. You may be given a problem asking you what would be the best method to separate A from B. And based on what you have learned in class, you should be able to propose one or more methods to accomplish that. There will be, as mentioned, some topics about which the questions are quite detailed. And by detail, that suggests that one, you know specifics, but you also need to know how those specifics tie together or work. It's not, so as an example, we will talk about glycolysis. This is a 10-step process, 10 enzymes, 10 molecules process the product, each becoming a substrate then for the next enzyme in this series of reactions. In some courses, some classes, it may be enough to know the names of the enzymes and the substrates and products for those 10 reactions. That will not suffice in this class. You will need to know how each of those reactions take place. You will need to know the features of the proteins. You'll need to know the features of the active site. You will need to know how the reaction is initiated. You will need to know how the reaction is controlled. There will be arrow pushing mechanisms that you will have to potentially draw out. So this is an area of focus. It's an area that requires then you're knowing something more substantial than the names of a few enzymes and substrate and products. So now that is one of the more extreme cases, as hemoglobin is, where you need to know lots of details. But those types of topics are fewer, but we're going to cover them in greater depth, and consequently the expectation is that you will know them in greater detail. Other questions? Yes?
So do we work with a lot of reactions in this class, or is it more about concept-based? I'm just curious.
It's mostly concept-based. We will have some specific reactions. There will be specific mechanisms that you will be expected to know. For example, we will talk about an enzyme called chymotrypsin. It is just simply a digestive enzyme, has a rather pedestrian function, but it is extraordinarily interesting in how it accomplishes its reaction. And so it becomes very instructive to see how the protein is able to facilitate something that naturally would not take place in the absence of the protein. So, just as an example. Okay, we need to move along. We're 15 minutes into the hour and we haven't talked about anything yet. Okay, I am going to move the slides for a few minutes. We'll come back in just a minute and talk. We'll use the board. Let's see if I can get. Oops. Okay, last class we had talked about hydrophobic interactions, and so just going to come back, touch on this in a specific context. In this case now, on this slide, you're looking at a fatty acid. You can see that there is a head group here. It is a carboxylate. It is negatively charged in an aqueous solution at physiologic pH. And there is a long hydrocarbon chain that is attached to this carboxylate. This region is very hydrophobic. The tail of this is very hydrophobic. And shown here are these ordered water molecules surrounding the aliphatic part of this fatty acid. And off here to the right and left are water molecules that are rapidly tumbling about, forming and breaking hydrogen bonds every 2 times 10 to the minus 11 seconds it's incredible how rapid they are interacting one with another. Now, notice what happens here. Now we have 3 of these fatty acids. So, and we are going to, you'll notice each of them has this this monolayer of ordered water molecules surrounding it to begin with. But if we bring them together, notice that the water molecules along those surfaces of the fatty acids that now interface, touch one another, are displaced. And all of these water molecules then are moved from being ordered to disordered. And in that way, entropy and energy release is increased. And this now becomes a highly favorable process. We refer to these water molecules surrounding now the 3 fatty acids together still as a hydration cage. And as long as that hydration cage remains intact, it will cause those 3 fatty acids to clump together quite tightly. We call these hydrophobic interactions or hydrophobic bonding even. There are really no covalent bonds formed. There's really no attachment between those hydrocarbon chains on these 3 fatty acids. But the hydration cage is constantly compressing those, pushing them together, not due to repulsion, but this drive to reduce the number of ordered water molecules surrounding those 3 copies. And ultimately, you can form micelles, you can form these collections, these spheres that are made up of fatty acids. Here's another example. This now represents a substrate binding to a protein. The substrate can be thought of as a smaller organic molecule. It could be a sugar, it could be something else that's going to be acted upon by the enzyme. And depending on what the surface of the enzyme is like, typically hydrophobic interactions play a role in substrate binding. That is to say, if the surface of the substrate is hydrophobic and has ordered water molecules present, and the part of the enzyme has a hydrophobic surface with ordered water molecules. If we bring these 2 together, then we reduce the number of ordered water molecules, giving rise to hydrophobic interactions between substrate and enzyme. Yes?
So the enzyme, is the binding site the only part that is hydrophobic? Is the whole thing hydrophobic?
It depends on the enzyme. Sometimes the interactions are not hydrophobic at all. You may have a phosphate on your substrate interacting with an amine, a positively charged amine group, or amine groups at the active site of the enzyme. In other cases, the substrate is largely hydrophobic, and the active site, the binding site, likewise is hydrophobic. So it's usually a bit of both. So hydrogen bonding, ionic interactions, and hydrophobic interactions are fairly common features of these interactions. Yes?
You found some hydrogen bonds there on the substrate of the enzyme.
No, these are not hydrogen bonds. These are, well, some may be hydrogen bonds, but mostly it's these hydrophobic interactions that are taken. It really depends on the active site. So, okay. All right. I want to now
He's not very good
go back to the board. So let me drop the screen here. that up as full screen. No, still. That's right. They're still seeing,
So they're just-
they're just seeing the camera. Okay. Okay, we're going to now talk about acid and base chemistry. Just a very brief review of this. And let me give you a reason then for going back and considering acid and base chemistry. It turns out that when we talk about molecular interactions, we talk about a range of different types of interactions that are important for binding one compound to another, one protein to another substrate, to enzymes, proteins that form a complex. Some of these are ionic. By ionic, we're simply talking about opposite charges, portions of molecules having a positive or negative charge, attracting each other. And it turns out that when we're talking about, we're outside the context of metal ions, when we're talking about charged species, we're really talking about acid and base chemistry. So that's why we're going to spend a minute and talk about this. So for our purposes, biology takes place in water. And so we are going to be talking about a particular kind of acid and base chemistry. This is called Arrhenius acids and bases. And basically, an acid interacts with water to form a hydronium ion and a conjugate base. Now, what I've written here is a weak acid, and effectively all the acids in our body, all the bases in our body are weak acids and weak bases, with one exception, and that's gastric acid, which is just hydrochloric acid. And the reason these are weak or considered weak is that they don't fully ionize, they don't fully react. So only a fraction of the original acid will undergo reaction with water to produce hydronium in the conjugate base. When we're talking about Arrhenius acids, when we talk about the strength of an acid, we're talking about the concentration of hydronium ion. The more hydronium, the more acidic a solution is. Okay, we're always talking about aqueous solutions in this context. A base, on the other hand, is going to produce, so we have base, and this is going to generate a hydroxide. So in terms of describing what we consider to be a base, it is something that will generate hydroxide ions. And the basicity, the alkalinity of the species depends on how much of the hydroxide is produced. If we take something like acetic acid, only about 1% of it actually undergoes reaction to produce hydronium ion. That's why you can put oil and vinegar on your salad and it doesn't destroy your esophagus, okay, or GI tract. Okay, because now we're talking about an equilibrium, that is, we have concentrations of both reactants and we have concentrations of products. For any given acid, there is an equilibrium constant. And this is described as the ratio of reactants over, ratio of products over reactants, sorry. Okay, so we don't include water because effectively its concentration doesn't change. It's 55 molar before and 55 molar after, but you don't include solids and you don't include pure solutions in equilibrium expression. So this represents then our equilibrium expression. Hopefully this is familiar. Questions at this point? Let me mention that for water, you can actually have a acid equilibrium where you have water reacting with water to produce both a hydronium and a hydroxide. The Ka for water is equal to the products of hydronium versus hydroxide, which is equal to 10 to the minus 14 at a temperature of 25 degrees Celsius. So hopefully this looks somewhat familiar. Okay, so where are we going with all of this? Okay, with water, we can describe the concentration of acidity as a pH. And so for water, the pH is just going to be equal to the negative log of hydronium. So we mentioned that as this goes up, the solution is more acidic. Or this goes up, the solution is more acidic. But because of this negative sign here, the pH is actually lower if it's more acidic. So a pH of 1 is substantially more acidic than a pH of 4. A pH of 7, that is, if we have equal concentrations of hydronium and hydroxide, we have a neutral solution. And the concentrations then of these are equal amounts of acid, equal amounts of base, neutral solution. All right. Okay, questions to this point? All right, then let me take, yes.
So in the Ka for water, you just put it over H2O.
You never use pure solutions or solids in equilibrium expression. So.
Okay.
All right, one final note here. There is also something called a pKa, and it is equivalent or analogous to this. It's going to be the minus log of the acid equilibrium constant. So whatever this is, the pKa is just going to be a minus log Ka, which is represented by this ratio of products over reactants. Okay. So let me give you now one other parting. We're going to consider in chapter 3 amino acids, some of which, so these have side groups, some of which are ionizable. That is, some of them can act as acids or bases. So let me give you a kind of a rule of thumb regarding weak acids and weak bases in specifically side groups of amino acids. So if we have a pH that is below the pKa of an acid. So this is the case for the acid. When the pH is below the pKa, we're going to have predominantly protonated species. Why is that? Lower pH means more acid, more hydronium. Consequently, we shift the equilibrium to more protonated species. For an acid, the charge on an acid that is protonated is 0. Now, as the, but for a base, when we have additional acidity, the charge on this is going to be +1. On the other hand, if we have a pKa above, more basic than the pKa, then the charge on the acid will be -1 and the base will become neutral. Notice that acids behave in a very particular way. They can either be uncharged or have a negative charge. Bases, on the other hand, will either be positively charged or neutral. You can't make an acid really, so this hopefully will help us determine whether something is charged or what the net charge on a particular molecule is. Okay, questions? Okay, the final thing I want to talk about related to chapter 2, final thing is buffers. And so a buffer, does anyone recall what the definition of a buffer is? Yes. Okay, you're right. So we have a weak acid. In this case, let's choose a specific one. Let's say that we're dealing with acetic acid. To form a buffer with this, we need to add relatively equal amounts of its conjugate base, not just any conjugate base, but its conjugate base. So here then we would add this conjugate base is going to be this, and you can do this. You can buy sodium acetate, you can weigh out 1/10 of a mole of it, and you can add it to acetic acid. You can measure out approximately 1 mole of the acetic acid or 1/10 of a mole. If you combine them together, they form a buffer. A buffer tends to keep pH in a very defined range. It tends to keep the buffer, it keeps the pH relatively constant in any given solution. Now, in our bodies, we actually have 2 extremely important buffering systems. One's in the circulation. Does anyone know what comprises the buffering system in the circulation in the blood? Yes. Okay, bicarbonate, and specifically, we are talking about carbonic acid. So you can get this wrong, I'm not careful. So we have carbonic acid and we have bicarbonate. So the bicarb is here, and the carbonic acid is here. Carbonic acid is an extremely weak acid. It has a pKa of about 7. Bicarbonate is slightly basic, and we have relatively equal amounts of carbonic acid and bicarbonate, and this buffers our blood to a pH of about 7.4, 7.5 in a healthy individual. Inside the cells, we have a different buffering system. Don't even know what constitutes the buffering system inside cells. Well, it's phosphate, okay? And we have then 2 species that are going to buffer this. We have the diprotic phosphate and the monoprotic phosphate. And these, again, form a buffer with a pH of about 7.2 to 7.4, depending on the cell in which they are located. So these two buffers are extremely important. Let me just give you an example of why this would be important, and we'll talk about one. So let's say that we're talking about enzyme activity here, and over here we're talking about pH. And let's say these are pH units here, and let's say that this one is 8 and 6 and 5 and 7. You would see that in most cases, enzyme performance is geared to a pH that is very close to physiologic pH. If you differ much, even a few tenths of a pH unit away, you can see that there's a dramatic decline in function. An example of this is the situation with somebody who is hyperventilating. Okay, so let's go back to carbonic acid. Carbonic acid is formed from CO2 interacting with water, producing carbonic acid. Carbonic acid, in turn, will react with water to form hydronium ion and bicarbonate. So what happens with somebody who is hyperventilating? Yes? They are blowing off a lot of CO2. So here's CO2. So if they're expelling CO2, then we're going to shift the equilibrium to replenish the CO2. That means that this carbonic acid is going to decrease as well, okay? Which means that we are going to lose the hydronium ion. So in effect, we're going to lose this. That means all of these equilibria are going to shift in such a way as to try to compensate for that. So in the end, we end up with less hydronium. That is to say that our pH actually goes up. And it doesn't have to go up very far before somebody begins to feel faint, and they can actually have a syncopal episode where they pass out. What do you do to sort of help in this situation? Yes?
Breathe into a paper bag.
Okay, breathe into some kind of paper bag container so that they don't lose the CO2. They rebreathe it rather than having it be diluted in the content of a room or something like that. You have them breathe into a bag. They rebreathe this, and so they maintain CO2 levels, they maintain acidity, and hopefully they are able to calm down and without passing out. Okay. We are quickly running out of time. I want to go back to slides here for just a sec. Okay, I have a question for the class, and we may not get far beyond this, but so here is a slide that lists out pKa. So let's use the feature of this. So this pKa here is for the acid group on the amino acid. So the amino acid has both an amine, which is a base, we have a carboxylate, we have a side group, not specified here, and we have a hydrogen. So we have this tetrahedral center, but there is an amine, which acts as the base with its lone pair of electrons, and we have a carboxylate, which acts as an acid. So the pKa here for one copy of alanine in solution is 2.34. Its base species, the amine group, has a pKa of 9.69. Now, if I combine, if I form a dipeptide, I react one amine group with one carboxyl group to form a peptide bond between two copies of alanine. Notice that something happens to these pKa's. This pKa now has become higher. That is to say, it's actually now a weaker acid, and the pKa of the amine group has been reduced. So over here, indicating that now the base species, the amine group, is acting as an even weaker base, less likely to pick up a proton than it was as a single copy. And you'll notice that as you add additional copies of alanine together, that we get a higher pKa for the carboxylate on one end and a lower pKa for the amine group on the other end. So the question is, what's happening? Why is this the case? I think I'm going to leave that question, and we'll come back and discuss it next time. We will be talking about chapter 3. We'll be talking about amino acids and the formation of proteins next time. Let me move this story forward a little bit. I had mentioned last class that that I had participated in the 2002 Winter Olympics, which took place in Salt Lake City. I was a volunteer, and I was assigned to the Olympic Medals Plaza, which was a centralized location in the heart of Salt Lake City, a two-block area that had been set up to have a stage where the medalists would receive their awards, their medals, and a very public celebration. 25 to 30,000 spectators watching the presentation. They had live bands. Some of them, well, they had fairly well-known bands at the time who would come and perform. And they had fireworks at the end to sort of cap off the night. And this one night, it only happened once, I was at the VIP entrance. And my responsibility was to make sure that everybody went through the metal detector, and then I inspected any personal bags, backpacks, fanny packs, camera packs, whatever. And they would just set them on the table in front of me, and I was only a few feet away from, oops, let me go back. Sorry. So anyway, I was only a few feet away from the individuals coming into the Olympic Medals Plaza. I was particularly interested in the athletes who had medaled that day. Now, other team members who had not participated, not won medals that day, were already in the audience. They were part of this 25 or 30,000 people who were surrounding the stage. It was only the medalists who were coming through through this particular entrance backstage to be able to go up and receive their awards. And it was quite interesting. I mean, there were some that looked absolutely Olympian. I can remember there was the German four-man bobsled team. They had these really very, expensive, very fancy uniforms that the whole team wore. And to a person, they were about 6'10", and their shoulders were about, anyway. They came in with this kind of, demeanor that told you immediately that they were somebody very important. At least they thought so. And they kind of strode into the Olympic medals plaza. And, you'd look at them, you say, absolutely, that looks like a gold medalist, no doubt about it. They're ripped, they're tall, and they have won the gold for their country. But I was surprised. I had a 15-year-old Norwegian ski jumper who had won a silver in the ski jump. Now he was decked out in this very fancy uniform, very fancy outfit that the Norwegian team wore. But he was not. He was just excited. He was just, he looked just like one of my kids' friends. He could have been one, except for the uniform, he just looked like an average 15-year-old kid. He wasn't exceptionally tall, wasn't exceptionally built. He had kind of long, stringy hair. He was kind of goofy and excited and so on and so forth. And except for the outfit, you would have never thought he was an Olympian. An Olympian champion at that. And even there was also this other team. It was from some Middle European country, I don't know, Slovenia or someplace. And they didn't have fancy uniforms. They didn't have a big budget for the Olympics. They just wore black turtlenecks, black pants. They looked pretty scruffy, to be very honest. Some of them were kind of disheveled, and they had black parkas. They just, if they hadn't been coming through the Olympic, the VIP entrance, you never would have thought that they were athletes, much less Olympic athletes, much less medalists. And so this got me to thinking, and I began to realize, just out on campus, we pass by people all the time who don't look particularly Olympian or don't look necessarily like champions, but may in their own right, may be one of a kind, really remarkable in their particular realm of influence. They may be by far and away the best listener or the best friend or the most compassionate person, the most caring, the most consistent, the most hardworking. You name the category, you name the event, and they may be Olympic, but you may pass by them every day and never realize that you're walking among champions. So today, I encourage you to consider the people that you go by every day, that you visit with, that you see at the bookstore or elsewhere, and wonder if they may not be champions in their own right. Thank you.